Okay, so let's take a look about this one. And we were talking about the structure last class. So today, now I'm going to show how to produce the numbers here. So they are actually the digit that we are using. So we can add more digit when we need more space to accommodate records. And we can also do the opposite way, use less number, and if we have less number records here. Okay, so the local one here, D prime, basically specify how many digits I have used. So the global 3, then how many I have used. Like this case, I use 3. But in this case, I only use 2. So you can see this one said bucket for record hashing value start with 0, 1. And regardless, after 0, 1, right? And there are many other digits possible, but I don't consider, no matter they're same or different, as long as they start with 0, 1, they end with in this bucket. And the global one always more than or equal to the local one. Okay, so let me show you one thing that you understand what's going on. That is how to do insert operation on this structure. So when we talk about insert, if we have a space, say for example, I want to insert a record, and I calculate how I apply the hashing function. I get a result, and for the result, I see I used binary representation for the result. Okay, and they have things like, for example, 0, 0, 0 as the beginning, and maybe something else. But since I'm only considering starting with the 3 number right now, so if they are starting with 0, 0, 0, they end with in this bucket. Okay, and so if this bucket has a space, then easy, just go ahead to put a new record in the bucket. That's all, right? When we do insert, so it's very efficient. So what happened is, what can be issue is if I insert something, right? And the bucket itself is supposed to insert in a particular bucket, but the bucket has no space to add any new record. And that's the things called overflow, right? Means you have no space, where can I put it? Okay. So we call the overflow of a bucket, and we are going to see how the system can accommodate this new record in 2 situations. One is the D prime less than D, another one D prime equal to D. Okay, so this is the local one, right? Less than global and or equal, and to see what can we do. So go back to this one. When we when we have the case of D prime, I probably should use another one. Let me think. Well, I can use this one. Okay, so when we have the D prime less than D, right? And this is the case that we can do something called bucket splitting. Okay, how to split them? So for example, I want to insert something into this bucket. In other words, my hashing result start with 0, 1. Okay, and so we can see no matter it is 0, 1, 1, 0, 1, 0 or 0, 1, 1, right? No matter which one end with in this particular bucket. And so I want to insert something to here, but this one has no space. And we are going to split the bucket. So what we need to do is I'm going to take this one, okay, make this bucket split into 2 buckets. Okay, so this bucket is gone. Instead, I'm going to use 2 buckets instead of 1. And for this bucket, I want to, for each of the record inside this bucket, I'm going to see what is the third number, right? So this one only using 2. So if the bucket hashing, the result of the hashing is 0, 1, 0, right? Okay, so remember each hashing result can be presented in many 0, 1, 0, 0, 1, things like that. And I only want to see the top two at this time, but now since I split it into two, I need a 3-digit. So I'm going to take the next one. So this is 0, 1, 0. So if I have this record, right, they started with 0, 1, but the third digit is 0, then go to this bucket. But if the third one is 1, then they go to this bucket. So this one bucket, for each of the record here, they are going to locate correspondingly to different places. Depends on the third one is 0 or 1. Okay, so let me get rid of this. Okay, and according to that, they are going to split into 2 buckets. So since 1 bucket is not enough, we're going to split into 2 buckets. As a result, you can see this one originally point to here, and this is not there anymore. Instead, this one should point to here, right? That's the bucket start hashing value start with 0, 1, 0. And this one, right, this particular one, of course, cannot point to here because it's not there. And we're going to point to this one here. So now you see why some of them with 3-digit, right? The D prime 3, right? Some of D prime 2. It's just because things like this originally only 2 because we don't have a lot of records. Now we have more record and more record inserted. Then eventually I'm going to split, and now the D prime here, this one, the D prime equal to 3, and this one also D prime equal to 3. So easy way to know what is the number of D prime is you want to see how many digits they use. So they always start with, right? So they start with that, then that's 3 digits. So that's D prime equal to 3. So you can imagine that when we insert more to this, more and more, this one can also split, and then coming from 2 to 3, right? Okay, now the issue is what happened if they all become 3, right? So for example, the bucket already have 3, right? And then they are another one try to insert into like the D prime equal to 3, and we don't have space. And how can we do that? And you may think, oh, I'll do bucket splitting. And yes, you do bucket splitting, but however, you're going to use more than 3 digits, and that is more than the global can accommodate. And this means this direction here need to be doubled also in order to accommodate that. And so that's actually this case, right? So for we have something already equal to global D prime equal to D already. And what we need to do is we need to double the directory. Okay, and we use the extra bit to distinguish 2 new buckets there. Okay, so let me show you how to do that. So this particular one show you when we still have extra bit to use, right? Extra digit to use, how to, but if we don't, what can we do? So let me get rid of this. Hold on. Okay, so now let's see. Suppose I want to insert something to the first bucket, right? So I want to insert something to here, and this is already full. Okay, so we don't have any space to add anything to here. And we know our logic is, I can split this one into 2 buckets. and then using, so this is 0, and I using the fourth digit. Say this is 0, this is 1, and we will to put this in. However, the directory only have 3, so you don't have a pointer correctly point to here anymore, right? No way you can do it. So that's why we want to double the directory. And I'm going to show you how to do. Okay, and so let's see. First of all, I need to remember the previous case. So I need a 4 digit, right? So now only have 3. So in order to have a pointer point to here, you have to have a directory called 000 and another one 001. So in order to do that, we double the directory, and the double the directory, we're going to have, so let's see, 000, right? And the 0 and 001, right? So originally they actually they only using 3, so they all start with 000, now become that. And then right, have this. Okay, right, and to run out of space. Almost there. Okay. All right, so that's what we have here. And this part is this, okay? So what I did is just like a bigger version of it. And then remember, we only care about, our issue is this one, right? We're going to split this one into 2, right? And let me save this. Why it doesn't allow me to save? Oh, it's okay. So we'll do later. And so I have this, and I'm going to, after I double this, right? So originally one bucket is going to split into 2, and D prime become 4 right now, and the global equal to 4 right now, right? And so this is the one, this is the bucket, right? And with the hashing value start with 000, right? Okay, and then the next one going to be D prime equal to 4 also, and this is started with, let me write down here, 00001, right? Okay, so let's see, that's what our split is, this given one, according to the 4th digit, where to split. And what about the rest of them? Okay, so remember, the benefit of this is it's not dramatically change everything. It only changes the things necessary, like, for example, the bucket here. This, every single record here stay the same. And so the structure of everything from here to here is the same, but just because they directly change, you just have to change the pointer point to the right place. And remember, to change the pointer, basically this is mean the value of which you go, right? That's the only thing you need. So it's not expensive. You're moving record between blocks, they are expensive, right? So this part stay the same, so that's why it's not expensive. So let's put the rest of them in. And the next one is here, right? So we use a 3 digit here, right? So that's why no matter this one or this one, eventually end with D prime equal to 3 in this, right? And the next one, if we go to, so this is a 001. And this green color one is this one. Okay, so just finish this one. So now the next one is the D prime equal to 2. And that's 01, right? So let's see which one is 01. We have 01, 01, 01. So all of them 01, right? So we're going to have 1, 2, 3, 4, and that's D prime equal to 2, and that's 01, right? Start with that. All right. And then the next one is, okay, so the next one is also 2, right? And so what we have here is 1, 0, right? Hold on, let me make sure. This is 1, 0, right? So 1, 0, 1, 0. Right, so I also have 4 of them. 1, 2, 3, and 4. And this D prime equal to 2, and this is 1, 0. Okay, almost done. So now you can see they don't change anything, right? Just the directory change. And this 3 and this 1, 1, 0. So 1, 1, 0, 2 of them, right? So this one and this one. D prime equal to 3, 1, 1, 0. And the last one is 1, 1, 1. So go to here and D prime equal to 3 and 1, 1, 1 here. Okay. So now you can see why this is called a dynamic, because dynamically, when we have so if this is the current structure, when we insert something, depends on, insert to something like a D prime less than that, or D prime less than D or equal to D, we can have like a different kind of structure change. Like this one, we actually double the directory. So you can accommodate much more bucket than before. So that's also the reason why this kind of thing form things like this structure. Whenever we have more things, we can split. And similarly, if we want to reduce the space upon deletion, we can also reduce how many. Okay. So that's what we have for this. Okay, so that's for the external hashing. Okay, so another concept we are going to learn is called the two-phase multi-way merge sort. And this particular one, so you learn the sorting algorithm in 130, right? All of them, they are memory sorting algorithm. And this particular sorting algorithm is basically consider the size of the input. So this is whatever we want to do sorting, and this is the size of the memory. So this is bigger than that. So whatever you learn in 130, they are memory sorting algorithm means suppose things can fit in memory, then you use the sorting algorithm to do that. But in the case we have like a database data, they are bigger than that. And how can we do it? So this is a way to do this type of sorting. And instead of giving you the details, actually, I think it's better just more like focusing on the concept. We utilize the disk multiple times to, put things back and then read things back, put things to the disk and read back in. We can produce something called the sublist to have a certain sorted result, and then using the second phase to merge them together into a single sorted list. So that's the concept. In other words, we divided this into multiple pieces of memory size. We do certain processing on each piece, right? And then we merge them back. Then we be able to do we be able to sort everything in the right order. Okay, so now we can move on, okay, to the next one, and that's the indexing. Okay. Okay. All right, so let's see a new chapter that is indexing structure for files. Okay, so why we want to think about this, right? So first of all, we already have primary storage of files. So we already have file, for example, they organized in sorted way or unsorted or like hashing way. So already have it. And suppose we don't change the structure of the data files. So this is the data file. So like this is student record, right? They are sorted by student ID, for example. So suppose we don't change this, then our ability to do things like a search is limited. Right? If I want to search students' major, I have to do linear search, right? So it's not that efficient. The question is, can we build something additional, right? So not changing this at all. Instead, we're building something additional, and we can use this additional things to access to those data files and to make this kind of operation more efficient. So can we do that or not? The answer is yes. And that's actually leading to something called indexing. Indexing allows us to access different fields of the data files more efficient. Okay, so let's see the structure wise. We can have a single level index structure with two things. One is order the index file. Okay, so like actually I can draw again. So this is my index file. The index file itself can be more than one blocks. Okay, that's fine. And we can have many blocks of data file. This is a big one, and this is a small one. This is small and easy to do binary search because this is ordered. Okay, and for each of them, we have a particular field we want to do indexing. And then we have a pointer point to the actual location of the date of the data file, right? And then we can using this to access the data file directly. So that's basically the structure. So if we think about index, we actually utilize the things beyond the database system, right? Like your textbook, right? So when you search something, of course, one way you can search is using table content, but table content is very high level, so you don't have everything, right? Every single topic. Usually at the end of textbook, you have something called the index, and the index file is much smaller compared to the whole textbook, right? And that one has a lot of keywords and critical items, those important topics, and you can search them because they are by alphabetical order. So for example, I search relational algebra, union operation, things like that. And so from there, you can go to, for example, page 200, and that's actually mention relational algebra, union operation, things like that. So we can search a small files, right? Like a last couple pages of your book, in order to tell me, okay, in order to know, okay, for this particular one is in page 200 and this here. So I just go to that particular page and the union operation is somewhere on that particular page. So this is very similar when we search them, right? And we actually will search the keywords here, right? So this is not called keywords, right? You think about textbook, and then we will to find the location. Okay, so that's the concept, the structure here. And so we also have a term called the dense index or sparse. So dense is every single index record. So this is index record. It is corresponding to every record in the data file. And this is the one called the dense, just because every single record in the data file going to have something corresponding here. And I'm going to show you an example of this. Another one is a sparse index. Okay, so it has the index. So this is a smaller, how many number of this is smaller than how many appear here. So this is kind of easy to understand, right? Like our textbook, you only have like a couple page of words, rather than a lot. And then the dense one, you may worry, is this like still serve the purpose? It will be too big. And actually, it's still okay because most of the data file, they are very big, also have many fields, and the index itself only 2 fields, right? Only pick whichever you want to do index. And also this one can give a lot of benefit in the case that like this is not ordered at all. So when you search things and using the index, it can save a lot of IOs. Okay, we're going to cover primary index, cluster index, and secondary index one by one. So first one is primary index. What is this? This is the one we want to specify an index on the ordering field of ordered file. Okay, so remember, important thing about primary index is when you build a primary index, the prerequisite is you have to have an ordered file. And so like this one, so this is ordered file, and suppose the name in this data file. So in this application, suppose name is unique. You don't have 2% have exact same name. And this, so that's why this is a primary key. Okay, so we use name as the primary key. And this data file is physically ordered based on primary key, that is name. Right? So primary index has certain restrictions. Okay, so what we can do is we build a primary index. Okay, once we have this requirements on the data file, we can think about what kind of index we need to have. Okay, so first of all, we do not need to repeat every single name in this, because if I have this name, like the first one in the first block and this one in the first record in the first block and first record in the second block here, if I search something like this one, when I see this, when I see that, I know I'm going to possibly have a record between 2 blocks, and that's something in this block, right? So since they are ordered, so name probably not that easy to do, if you think about numbers. So if I have 1 and the next one is a 5, if I search number 4, I know this will be in this block, right? Because after that, you will see a 5 and further. And so that in that way, the index, when we're building the index, I only need the first record of each block. So in other words, I can build the structure like this, and it helps me to locate one disk block, and that block possibly have the record I try to search. And also possibly it's not there. And if it's not here, it will be not in anywhere else in the files. It's just because this is ordered. Okay, So let's see. So we order the key. So when we do that, we talk about like we have order files, and it's called ordering key field, right? Like name. And the ordering key field used to physically order the file record on the disk. Okay? And for the index files, we have two things. One is the primary key, right? The name is the primary key, and then the point to the disk block. And you may wonder, does it make big difference whether you point to the block or possibly point to the record? In this case, right, like this is probably easy way to see that you don't actually point to the record, you only point to the block. And actually, if you have a pointer to the block or point to the actual record, performance-wise, we don't see a big difference. Right? Remember, we have to load the whole block into memory to do processing. So the I/O time is 1 anyway. Okay, once you load the block into main memory, we can use main memory searching algorithm to search it. And once we do that, that is main memory time. So it's basically CPU using CPU time, not I/O. So that doesn't matter. So that's why usually we don't care that much about block pointer or record pointer. Although we'll have a difference because you have to search within, but it doesn't take I/O, and I/O is supposed to be much better, much bigger than CPU time. Okay. So go back to this. This is a pointer to the disk block. And we have, so we have a primary key and point to that. And remember, this is important also. So every single index record corresponding to one block. So if this one, say I'm going to have, for example, 100 blocks, right? And in this primary index, this one, I'm going to have 100 records. And they may be more than one blocks, right? So this is hard to say can be fit in or not. This is a smaller because I don't have other field, but still may not be necessarily fit into one block. Many cases, the index taking more than one block. So this is 100 blocks, and then we have 100 record. And this is example of sparse index. So more data files, this is each block many record, more data file records than the index records. Okay. So now let's see how we access a record, right? So the whole reason for building index is just speed up the way to search them. And when we access a record with the index, I want to load the index file first. Again, they usually take more than one block. And we search in the index file in order to find the right record. Okay, so if I found out eventually this is the one I need to follow, then I have to go to point to here, and I'm going to load this block correspondingly because the things I want to search possibly within this. So either within this or not in the search, no result at all. And so that's the way to use index. So whenever you have index, always search the index first and then utilize the index, right? Usually index how many blocks you take to search the index for IOs plus one more. That's using the pointer to loading the corresponding one. So what is the key concept of primary index? Okay. And one more thing I want to mention is the concept, the terms we use here, primary, clustering, and secondary index. This is according to our textbook. And when you use specific DBMS systems, okay, most cases when you create index, you don't need to specify what type of index you want to specify, you just say create index. But if you want to use specific term about which type of index, you want to see their user manual because some of them, they define things using different terms. Okay, so they mean the same thing, but they actually using different terms or wordings on the index names. So that's one thing I want you to pay attention if you want to use it. Okay, so let me quickly summarize the primary index here. For primary index, remember, if you want to build a primary index, you have to have order the field record. And based on that, you can only build your index based on the ordering field. So say, for example, this is the one order based on name. You can build a primary index based on that. Okay, you cannot build a primary index based on social security number. Okay, social security number is unique also, right? However, you cannot do that because this file is not physically ordered based on SSN. So you cannot build primary index based on SSN regarding this file. And we can build other type of index, but that's not called primary index. So I have something here. Basically, this is to try to show if we use an index, are we be able to have performance gain? Means, you know, the IO cost with index or without index, are they different, right? So the answer is using index can save can be a better performance, can save the IO cost. And this is actually the whole calculation is based on that. So we can have the things without index, and if we have a primary index, what happened? Okay, so if I do a briefly, let me see. So briefly, this is about, for example, I have a size of the block and the record size and how many total records there. And remember, we talk about blocking factor, BFR here. This one means how many records per block we can have, right? And if we know BFR, we will to know a file has how many blocks, right? B equal to R divided by BFR. R is totally how many records, and BFR means how many records we can accommodate in one block, right? Okay, and so if we have a file with B block, okay, so like we can calculate this way. And if we do binary search, you found the specific record need to be accessed. We need to access the log time. So that's how many block. And for linear search, we use the average rather than the worst case. And this is actually the worst case. And so we do this. And we actually compare something like the worst case, the big O, and also the linear search using the average half of it. Okay. And so in this example, the first one is we don't have index. What can we do? And in this case, since we also the data file is also ordered, so we still can use binary search on the data file. It just the data file is big, so that's why we take. So in this case, we actually take 12 records. 12 blocks to do that. So it's not bad because just because this is actually we can use binary search, and now that's primary index, right? And give the index structure of how many bytes for the ordering field and the pointer, for example, like this. And what we're going to do here is we actually spend the time to search index. And for searching index, remember one index related to one block, right? One index, one block in the primary. And eventually we take 6 blocks to search the index file, and +1, that means we can follow the pointer to get this. So eventually we using 7 blocks. And we don't see a lot of performance gain in this. Actually, hard to say 12 compared to 7. And it just all depends on how big everything, right? The size, everything. But this can show how this operation can do for primary index. And we'll talk about other type of index next class.